Welcome to the TechViews 1X flagship explainer. I'm your host, Jessica, and today we're diving into an absolute paradigm shift in AI. For years, right, AI was basically just a really fast autocomplete, but there's this quiet revolution happening right now in test-time compute, and it literally changes everything. Because today, the top models out there don't just blindly predict the next word anymore. They actually pause, they reason, they verify, and they even correct their own mistakes before they ever give you an answer. So think about the old era of AI. It was essentially a linear token predictor. If you gave it a complex math proof, it would just guess its way through, make a mistake on step 2, and blindly snowball that error all the way to a completely wrong answer. But the new era? It's like a glowing multi-branch reasoning tree. Instead of spitting out the very first statistical guess that pops into its head, the model is spinning up multiple possible paths in real time. It verifies them, checks its work, and solves the problem instantly. It's the difference between just blurting out an answer and actually taking a moment to think it through. And the engine driving all of this is something called test-time compute scaling, or TTCS. Now, historically, you know all the heavy lifting was done during the training phase, right? Giant data centers churning away for months. But TTCS shifts a massive chunk of that computational power to the exact moment you hit enter on your prompt, the inference phase. Basically, by throwing extra compute at the problem while it's actively thinking, the system can systematically evaluate and refine a bunch of candidate solutions before it shows you a single word. Okay, so how does this actually work under the hood? It's driven by something called Monte Carlo tree search, or MCTS, and it happens in 4 super fast steps. First selection, it picks the most promising thought to start with. Then expansion, it brainstorms multiple new potential steps from that point. Third is simulation, where it literally plays out those paths to see where they lead. And finally, backpropagation. It takes the final grade of that path and sends it back up the chain to update the scores. So in absolute milliseconds, the AI explores dozens of solutions, completely abandons hallucination paths, and locks onto verified logic. What's wild is how some of the new cutting-edge frameworks are optimizing this exact process. Take AceSearcher, for example. It actually trains a single AI to sort of split its personality into 2 distinct cooperative roles. First, you've got a decomposer that takes a wildly complex query and hacks it into bite-sized sub-questions. Then a solver swoops in, pulls the context, and answers those specific pieces. And the absolute best part? It's all graded by internal verification rewards. The model is quite literally grading its own homework before turning it in. But where exactly is all that extra compute budget going? Well, there are basically 3 structural regimes here. First, there's single trajectory scaling. That's just the AI thinking longer and harder on one single path. Then you have leaf-level scaling, where the AI generates a bunch of fully finished answers and basically holds a vote to see which one wins. But the holy grail is prefix-level scaling. This is where the model actively prunes unfinished, partial thoughts the second they look like dead ends. It chops off the bad branches before they even grow and waste resources. Understanding the mechanics of these technical shifts is exactly how you stay ahead of the curve. But let's be real for a second. Putting these shifts to work, that is how you build real wealth. The mechanics of AI are super fascinating, but the commercial reality of actually leveraging it for your business, that's the real game changer. So if you want to master AI reasoning, if you want to automate complex business workflows, and actually learn how to leverage AI to make money online, you need to go to techfuse10x.com right now. We are giving you the exact frameworks and the step-by-step playbooks that top entrepreneurs are using to scale their operations 10x faster. Head over to techfuse10x.com. Seriously, the link is right on your screen. Grab your edge before your competitors do. All right, turning back to the tech, let's introduce a massive twist here. We've established that giving an AI more time to think makes it smarter, right? But does more compute always equal better answers? Because right now, there's this really dangerous assumption floating around the industry that if you just let an AI think longer and longer, you'll infinitely increase the quality of the output. Well, the data totally shatters that assumption. What we're actually seeing is this crazy overthinking phenomenon. When you look at the numbers, the marginal utility absolutely plummets once the compute budget crosses a certain optimal threshold. In fact, if you push a model's reasoning beyond, say, 12,000 tokens on certain problems, you literally get negative marginal utility. The AI gets confused, it second-guesses itself, and it will abandon a perfectly good, correct answer just to hallucinate a wrong one. So yeah, overthinking can absolutely hurt. And the hardware economics of this are brutal. To put this into perspective, generating 16,000 tokens costs 32 times more than generating just 500. So not only is the model potentially confusing itself, it's literally setting your server budget on fire to do it. When you factor in costs, the optimal stopping point on these utility curves shifts dramatically to the left. Implementing aggressive early stopping strategies isn't just some neat coding trick, it's absolutely critical if you want to protect your data center budgets in the real world.
So, how does this change system architecture? Well, the efficiency trade-offs are super counterintuitive. We know that scaling test time compute with multi-agent setups, like mixture of agents, where a bunch of models network together, heavily outperforms a single agent just checking its own work. But here's the crazy part. Sometimes, simply using a massive 70 billion parameter base model with zero test time scaling is actually the most compute-efficient choice of all. Why? Because of GPU memory transfer times. Shuffling data around your hardware to coordinate a bunch of tiny agents can actually take longer and cost way more than just asking one giant model for the answer straight away. So it all comes down to finding that sweet spot. The data proves you really don't need to burn endless compute. If you optimize for a balanced, cost-aware stopping point, you can hit 97% of peak reasoning accuracy while slashing your raw compute costs by a staggering 40%. 40%! You just have to know exactly when to tell the AI, okay, stop thinking, give me the answer. To pull that off at scale, engineers are using system-level optimizations like negative early exit. Think of it like a ruthless manager. When an MCTS search gets stuck in a loop or goes down a rabbit hole without making any real progress, this mechanism just brutally prunes that trajectory. It cuts it off, reclaims that wasted compute, and reallocates it to a higher potential search. And that right there is how you prevent those massive long-tail latencies where you're just staring at a loading screen waiting for a server to respond. Zooming out to look at the big picture, here is the final verdict. These reasoning models and mastering how they utilize compute at the moment of inference, this isn't just an incremental update. It is the exact stepping stone, literally the bridge, to fully autonomous agentic software. We're watching AI move from just a tool that spits out a first draft to an autonomous worker that plans, verifies, and executes flawlessly, all on its own. So the only question left is, are you going to leverage this reasoning revolution, or are you going to get outpaced by it? Make sure to head over to techviews10x.com right now to grab our complete AI implementation guides and secure your edge. And hey, don't forget to hit subscribe for your weekly 10x Tech Edge. I'm Jessica. Thanks so much for joining me on this explainer, and I will see you in the next one.